All right, so we're going to be doing a lab today in which we're trying to figure out the best way to write the orbital notation for a set of transition metals primarily, for the ions of these transition metals. Now, when I say the ions of the transition metals, so far we've been writing orbital notation primarily for atoms that have all the electrons. There's no positive or negative charge. The positive or negative charge comes from removing or gaining electrons. Positive charges, like the 2+ charge on this copper, come from removing 2 electrons. Remember, electrons are negative and protons are positive. If you have more protons than electrons, you're going to get a positive charge because of that imbalance. So what we want to know is, what's the best way? What makes the most sense? How does nature tell us those electrons are arranged in the orbital notation or the electron cloud of this material? So we're going to be using a property of matter called paramagnetism. And what that means is, the more unpaired electrons there are in the electron cloud of an atom or an ion, the greater the attraction of that substance to a magnetic field. So we have a balance set up here. As you can see, what we have is a rubber stopper with 2 very strong magnets sitting on top. Now these magnets are neodymium magnets. They're very, very strong, so please don't play with them. They're also very brittle. It's easy to break them. But they're very strong, so you'll get a very good result. As you can see, I've set this up so I have tiered the balance now with the rubber stopper and these 2 magnets sitting on top. So you zero the balance, you place the rubber stopper and the magnets on the balance, and you press the tare or 0 button here, and now the balance reads 0. What you want to do is to find out just how much these salts are attracted to the magnet. So I could take these salts that I've got in these vials, and I could try to hold it very, very carefully, as close to this balance as I possibly could, and find out how much there is a change in the mass. But as you can see, it's really, really hard to hold it very, very steady and still hold it as close as possible to the balance. So what we've done is arranged a way to be able to do that so that you don't have to hold it with your hands. So here's the apparatus we've set up. And what I have is a ring stand. This right here is called a ring stand. This is an actual ring, and you've got a clamp that holds the ring in place. And I have the salt suspended from the string where everything is made of stuff that shouldn't be attracted to these magnets. And you have to decide with your group how you're going to arrange that. Well, the point is to get that salt as still as possible, as perfectly vertical as possible, and as close as you possibly can to the top of those magnets. You can measure the change in mass. Now, I've sort of arranged one here, and you can do it however, whatever works best for your group. Sometimes it takes 2 people to do this at one time. One person is actually looking and seeing how close you are, and trying to figure out, am I close enough, or do I need to get closer than that? And you just keep working at it until you've got it in a way that's perfect for your group. Okay? Try to get as close as you possibly can without ever touching it. We're as close as we possibly can to this without actually touching it. I want to move it back out of the way so it has no effect on the balance. Zero the balance again, and then very gently and carefully place this vial as close as I possibly can to those magnets without actually touching. So you can see just how close I am to those magnets. And I'm just going to let it settle down and stop swinging, and then make the measurement on the balance. As it slows down and gets really, really still, then I can see how close I am and get a good number. You can see that it's still moving around a little bit. You have to figure out which is the best number if that the balance is not sitting dead on one number or another. You have to choose which one it stays the longest to, which measurement, if it's a 0 or a 1 in the hundredths place, or which one you're staying closest to for the longest, and then you figure out what you think is the best possible measurement. There is nothing here that is going to be ever perfect. but you want to try to get the very best results that you possibly can. Then all we're going to do is compare those on a graph and see which of two graphs makes the most sense. Nature tends to follow patterns. We're looking for a pattern in its behavior. And one of these two graphs should have a better pattern than the other, and then from that we can make a judgment about which is the best system to use. Removing electrons from the highest energy level first, or moving them in the same order, the opposite of the order we put them into the orbital notation. So let's look at the orbital notation really quickly. We're really just looking at the valence level here, because that's where the action is taking place, in the valence level. So for manganese then, we have 2 electrons in 4s, and then 1, 2, 3, 4, 5 electrons in 3d. I need to do this in pencil so that I can erase to get to that 2 plus charge. So the way that we've been taught to do that, I've taught you to do that, is you put 2 electrons in 4s, then 1, 2, 3, 1, 2, 3, 4, 5. Okay, 4, 5 electrons in 3d. And then we need to remove 2 electrons. And we're going to do this in 2 different ways. Okay, so 1, 2, 3, 4, or 1, 2, 3, 4, 5 electrons here in 3d. All right, so here you're going to look at possibility number 1. Possibility number 1 is to remove electrons in the order you put them in. So I'm going to remove the 2 electrons from here and here. Possibility number 2 is to remove them from the highest energy level first. So I move them from here and here. So here I can see that I have 1, 2, 3 unpaired electrons, and here I can see I have 1, 2, 3, 4, 5 unpaired electrons. And then I'm going to measure the amount of mass change, and I'll put that in a graph, and I'm going to compare the 2 results. All the results for this type of removal of electrons and all the results for this type of removal of electrons, and see which one seems to make the most sense, because I know that in nature things tend to follow patterns.